have input the driller and the geology information for the example structure project. So we're going to go ahead and start inputting lab information for the example structure project. So I'm going to first open up this gINT KYTC training folder that's on my desktop, and open up the soil lab input, and then open up the example structure raw lab data. So this PDF has the information for the raw lab data that we're going to be entering into the example structure project. And this is basically just an example. These are example sheets made here at the geotech office of kind of how the flow of how we go about doing our laboratory data. So when the gINT file comes in and the lab samples come in, an extrusion log is printed out. And so this extrusion log has basic information on the hole number, the sample taken, and then moisture content, and a quick visual description. If that sample is a Shelby tube, number of samples that was made from that Shelby tube is marked, and then the pentrometer value that was obtained is marked. This request for testing is blank until the engineer fills that out, and then numbers to mark the samples that were used for classification are marked here on the far right. So for instance, the sample for hole 1001 at 2.5 feet down was given an ID of 1029, and so that corresponds to the 1029 number here. So this is a soil classification sheet for that particular sample. So in this raw lab data PDF, we have an extrusion log, we have the soil classifications that go with those that's marked on the extrusion log. We have a unconfined compression test that was conducted on sample ID 1029, and then a UU test. And then lastly, a consolidation test. So if we go back up to the extrusion log, you can see that they were marked for this hole 1001, 2.5 feet down, a UU test was conducted, or a QU test, apologies. And then for 1006, a UU test was conducted for 5 feet down. And then for that one, hole 1006, a consolidation test was conducted for 10 feet down. So that kind of gives you an overview of what's in the raw lab data for the example structure project. So we're going to go ahead and start inputting information into the gINT file. So I have the gINT file already open for the example structure project, and I'll scroll over to lab testing tab. And so for the lab testing, I'll start at hole 1001. For the example structure project, there was only samples collected for hole 1001 and 1006. The most important table when inputting lab information is the soil specimen table. Based on information you put into this table, it'll affect other tables inside of the lab testing table. So we're going to first start inputting information for the 2.5 foot depth for one hole 1001. So I'll make this a little bigger. So hole 1001, 2.5 feet down. Our description is here. So it's a brown and gray clay. No proctor conducted. The pentrometer value is 4.5. And then for the sieve, to see what type of sieve was conducted, so you select from this drop-down menu whether gravel was present when you did your sieve. So the gravel is based on the AASHTO classification, which is everything retained on the number 10. And so to see how to fill out this sieve drop-down box, and this is pretty important because this inputs quite a bit of information into the sieve table here. So we'll go down to the soil classification sheet for 1029. And we see, if you look on this mechanical sieve here, this is retain number 10, 4, 3/8, 3/4, an inch, 2 inch. So for this number 10, there was no material retained, so we know on the sieve drop down that there was no gravel. Okay, so moving on, and we'll fill out number of specimens for the testing and that kind of thing. Actually, we'll fill in number of specimens created now. So number of specimens refers to the number of specimens created from a Shelby tube. So not the number of specimens that were tested. The number of specimens that were tested is based on how many boxes are filled in for specimen number 1 test, specimen number 2 test. So we can see from the extrusion log that number of samples created was just 1. And we'll fill in the testing information at the end after we've already classified, after we already input all the classification data for the samples. And since the classification is pretty repetitive, I'm just going to be showing inputting of information for hole 1029 and 1034. The first one is inputting information for when a soil classification does not have a gravel portion, and then the bottom one is when it does have a gravel portion. So if you want to see, as you're going along through the example, if you want to look at what the actually input information, you can open up, if you go back to the soil lab input, if you go into this complete folder, you can open up this example structure here to see what the actual input values were. So going back to our first sample for hole 1001, we've input our pentrometer value, our description. It was no sieve and number of specimens created. So we'll go save that. And when you're inputting information, you have to put a value for the sieve type to save this table. So we'll go ahead and look at what type of sieve was conducted for the 5-foot depth specimen for hole 1001. And so we'll go down, scroll down to 1030, and you can see here that there was no gravel portion. So we'll go here and hit no gravel. And we'll go ahead and input information for that sample. So pentrometer was not conducted because it was a split spoon and it was a brown silt. So that's all you have there. So we'll save that. Then moving on to our natural moisture content, we'll input information for the 2.5 foot depth down. These light blue fields again represent values that will be auto-populated. So we'll leave this blank, and that natural moisture will be calculated from these values here. So we have our can number, which is 19. Our wet weight and our tear is 80.5, 73.4, and 45.3. So we'll save that. And that 25.3 water natural moisture content is represented here. So Atterbergs, we'll go move down to our classification sheet for soil classification ID 1029. So a little breakdown here. You have liquid limit, plastic limit information. You have your sieve analysis of your fine aggregate. You have the hydroscopic moisture here at the bottom of that fine aggregate. You have your specific gravity information, mechanical sieve for retained number 10, and then you have your hydrometer analysis information at the bottom right here. So the lab, the Atterberg table is a split table. It has the top table has information on the samples, and the bottom table has information where you input your Atterberg readings. you can switch between the bottom tables by selecting from the top between the rows of the two different samples at the top. And you can see as I switch between those, your Atterberg reference here changes. So I'm going to input information for the 2.5 foot depth down Shelby tube for hole 1001. And so I'm going to go down to the bottom here. And so my liquid limit is, so I'm going to be reading from my liquid limit data across here. So our wet soil in the can is 31.48, 24.85, 13.91, and number of blows was 26. So now I'm going to input the plastic limit information. So 17.67, 16.81, and 13.92. And so when the number of blows is not input here, it knows that it's a plastic limit value. And when there is blows, it knows that there's a liquid. It's a liquid limit value. So those are the two values you need to input. And we'll hit save. And this value is okay. It's saying there's no value here for number of blows, but since the program uses that blank to know whether it's a liquid limit or plastic limit value, that error is okay. So hit OK. And then it populates liquid limit, plastic limit, plasticity index, and liquidity at the top. So now that we've got our Atterberg's information input, we'll move on to the sieve. Because we selected in the soil specimen that there was no gravel, it inputs this weight of total specimen as 1, and that's referring to the mechanical sieve information. At the geotech office here, for the weight of fines tested, we always use 50 grams. We'll move over to our water content of our fine material, and that's specified here as our microscopic moisture. And so we'll input 30.39 and 29.13, and that's that information. And then we also need to input information regarding our mechanical sieve. And so we know here our mechanical sieve for all of the material retained above the number 10 was 0. So we need to input that 0 value here. And then we also need to input our mechanical sieve analysis of our fine aggregate. So that's the weight of our soil. So 0.17 and 0.26. And so when we go about saving this, it'll populate those values, and then it'll populate our water content of our fine aggregate. Okay, moving on to our specific gravity information. Specific gravity is here on the soil classification sheet. So we need to select our depth, which was 2.5 for this sample. Our temperature was 72. Weight of our sample was 29.15. Water weight was 164.67. And water weight plus soil is 182.4. And so once you save this, it'll populate information in the hydrometer table. So we'll save that. And so now our specific gravity is input for that sample. Okay, for the hydrometer table, all of the calibration factors here at the top are input once you select your hydrometer ID and you save it. And so I'll go ahead and right click and hit field properties so you can see some information about this field. So this field is coming from the library file, coming from the library table, hydrometer calibrations, and you must use this lookup value. So for you to use this table properly, you need to input your hydrometer calibration factors into that table within the library table. So once you've input those default values, you can go click down, and I'm going to use the KYTC 707901 drop down, and then when you save, it populates the type, your temperature units, calibration, intercept, and all that good stuff. So now your defaults for that particular hydrometer is input, and so now we can start inputting here at the bottom table our hydrometer analysis information. So for the 2-minute time, hydrometer reading was 50, our temperature was 68. For 60 minutes, it's 39, 68. For 250 minutes, it was 30 and 69 degrees. For 144, 1,444 was 23, and temperature was 69. So we'll hit save, and it'll calculate that particle size in percent finer. So now our soil classification is complete. So sieve type, no gravel. And you can see our soil classification was classified as a fat clay, high plasticity clay here. And then you can see our ASHTO symbol. So it has some more information on our specific gravity, our activity, and then some percentages that our particle size is at. So that's pretty standard. You can kind of go through and input the information for the rest of them. I'm going to fast forward to the soil classification for 1039, and the only reason I'm showing that one as compared to this one is that that one has gravel as compared to no gravel. The rest of the samples, the classification samples up to that sample, are all have no gravel. So I'm going to fast forward from here to the soil classification for 1034, which is the last sample for hole 1006. Okay, now that I have all of the soil classifications input, except for the very last one, I'm going to basically go through inputting the last one, and that sample has gravel attached to it. So for the classification ID number 1034, I'm going to start inputting that information. And if you want to see, as you're working through inputting this information, you want to see that you're getting the inputting the correct values in the correct spot. Like I said, just go in to the KYTC training folder here, KYTC training, soil lab input, go into the complete tab, and you can open up that example structure that's already complete. So going back to where we were at, for 20 feet down, input this classification, or the visual classification here, brown and gray sandy clay, input with gravel, hit save. And I'm also going to input number of specimens while we're at this table. So I know there's one specimen for 5 foot and one specimen for 10 foot. So I'm going to put here 1, 1. Hit save. Okay, now moving on to our natural moistures. I input the value for the last one, 20 feet down. So here, this can number was 22, which is here. Wet weight was 79.2, dry weight 75.9, and then our tare weight was 10. Or not tare weight, that's moisture content. Tare weight was 45.5. So our moisture content is 10.9, which is this value here. So going on to our Atterberg, I'm going to input our Atterberg information. So I'll scroll down to classification ID 1034, which is right here, 1034, and put our Atterberg information, 30, 26.82, 14.47, and 24, and 19.5, 18.68, and 13.7. 0.5, hit save, and that's okay. Okay, populated that. Go to our sieve table. And so this is where it's a little different because this sample has material retained on the number 10 and above. So before, this weighted total specimen here just been input 1, basically as a holding value. Now we need to input our total weight of our sample that was dry sieved. So that's 603. We still need to input our weight of our fines tested, which was 50, and our hydroscopic moisture information. 31.04 and 30.58. And now we need to input of our weight of our sample, and that was retained. So it passed 100% on the 3/4. The 3/8 is 24, 9, 6. Number 40, which is this sieve here, and 200. So 0.5 and 16.4. So we'll hit save. So now I calculated those percent passing, and that's pretty much the only difference, is that you need to input your weight of your total specimen. You need to input your values for material retained above the number 10. So moving on to our specific gravity, select our 20 feet down, 72 degrees, specific gravity here. So 30.6. 139.57, 158.15. Save, and it populates information in this hydrometer. Save that. So now we input our hydrometer information. 2 minutes. Reading was 34, 68. 60 minutes, it's 18, 68, at 250 minutes was 15, and 69, and 1440 is 12, and again it's 69 degrees. Hit save, populates those, and so now we have all of our soil classifications complete. You can see the last sample was a low plasticity clay. So now, since we have all our classifications input, we're going to start inputting information for the testing that was conducted. And so I'll go back to sample for hole 1001, and I'll scroll back up to the extrusion log. So on the extrusion log, the engineer will fill out here what kind of testing he wants for each sample. And so we can see there was a 1 marked for QU for the 1001 hole at 2.5 feet down. And so that QU test, that sheet is associated with that 1029, and so that's at the bottom of the PDFs. So that's this sheet here. So 1029, you can see our information for our sample, our depth 2.5 feet down, hole 1001. So we're going to be inputting the information from this sheet into gINT. And so now, to specify that this test was conducted, you go into specimen 1 test, and there's a QU. And when you save this, there will be a value that's automatically input into this QU table here. And so we'll save that. So now in QU, there's a 2.5 foot depth sample for a Shelby tube. Now we can input this information. And so in the QU table, you can see some of these light blue fields. So what is a little different when we updated here recently is that we inputted both dry and wet densities for all the strength tests as well as the consolidation test. And so you can input a value into either the dry density or the wet density, and it'll calculate one or the other. We did this just so we have both in the same table. So I'll go ahead and start inputting this information. So our moisture content is here. So that's 18.9. Our dry density has wet density, so I'll input the wet density and our dry density will be calculated. So our wet density is 131.9. Maximum stress PSF is 4,000, which is right here. 4,024.81. Strain at failure was 2.17%. It didn't reach 10% strain. And so when we save this, this report file name will be generated. And so what that is for is so that the GINT file can associate that name, that PDF file name, to this particular test. So it's important when you're filling out, when you're keeping the records, the raw data for the sample, that you name the PDF the report file name that's generated in this box here. And so I'll hit save. You'll see the dry density calculated. And then you have your report file name here. So just name your PDF that houses the raw data for that particular strength test, that name. And so that way the GINT database can associate this particular row with that raw data file. Okay, so that's our QU input. And now we'll go back to soil specimens and go to hole 1006 and scroll back up on our extrusion log, up to our extrusion log. Let me go the other way. Okay. So we have two more tests that were conducted. Two more tests, this UU test and then a consolidation test here. And so this UU test was conducted on the 5-foot depth sample for hole 1006. So we'll scroll over, 5-foot depth. We had one sample was created from the Shelby tube. And so we want to select here a UU test. And so again, when you save this value, it inputs a record into the UU table here. And so now we'll scroll down. We have the pressure that was specified here, number of samples, and this is the ID number that was associated with that test. So 1031, so we'll scroll down to the bottom here, and 1031, this is our UU sheet. And so we'll input some information here. So our maximum stress, this is given here, our peak deviator stress. It's given in PSI. So we need to convert that value. So it was in 20.127, and then we need to multiply that value by 144. And so that's our maximum stress value. So I'll input that value. So it was 2,898.28, actually 29. Our strain at that point at failure was 3.22%. Our moisture was 13.62. Same thing as our water content. Our dry density is given on this particular sheet. It's 118.17. Our wet density will be calculated. Something new again with the update, recent update, is we have cell pressure in here now. So our cell pressure was 21 psi. It didn't reach, actually it did reach 10% strain, but it wasn't our peak strain. So we're going to leave that blank, and then that report file name will be generated. So there we go. We have our wet density that was calculated. And so that's our input of our UU information for the 5-foot depth sample for hole 1006. And so our last values to input for the lab testing for the example structure is the consolidation test. So we'll go back up. We'll see which sample that consolidation test was run on. So consolidation test here, 1, and that was for the 10-foot depth. So here, so input consolidation here, and again, when you save this table, it'll input a record into the consolidation table. Kentucky consolidation, so now you have your record there. So we'll scroll down to our consolidation test here. I'll make this a little bit bigger. So we have our saturated moisture, which is 30.3, our natural moisture, which is 24.7, our dry density, which was 91.1, our wet density will be calculated. Your PC value is the maximum past vertical effective stress that the sample has felt. And so you have your PC in tons per square foot there, so it's 4.84. Your compression index is 0.14. And then your recompression index is 0.01. Your starting void ratio, your E naught is 0.793, and again your field name will be generated, and that's the value, the name that you should give the PDF that houses the raw data for this consolidation test. So we'll hit save. Wet density was calculated, and then our report file name was given here. And so that's inputting all of the raw lab data. And so basically I'm going to show you that was all the raw lab data for the example structure project. And so now I'm going to show you some output of that extrusion log that we've been reading off of. So if you go to output, graphic tables, and Kentucky extrusion log, we'll preview that. And this is that extrusion log that we've been using. So basically, when you get your moisture content input and your soil, visual soil descriptions, and then how many samples you've created from your Shelby tubes, you can basically use this to keep track of your indexes for your classifications, and then what kind of testing you want specified for the particular samples. And so that's it on inputting the lab data for the example structure project. So thank you very much.